So in this particular example, as rightly pointed out already, why we are discussing this is the first line, that for asymmetric key cryptography, we actually use the prime numbers. Now, we all know about prime numbers and how they are used, or the significance of it and all. But what we need to know is that, again, in the same manner, that if suppose we have specifically prime numbers as the modulo operator, then we can apply certain theorems on top of it so that our calculation becomes relatively easier. All right. So keeping that in mind, these are the specific group sets that we consider on the go. So we usually have three parts of positive integers which we can divide into one, primes and the composites for that matter. I guess the definitions are known to you, so there is no point of discussing in that aspect. Usually a prime, which is a prime number, is divisible by itself and 1. And as you can see, integer 1 is not a prime number. As per definition, as a prime must be divisible by two different integers. Alright, so that's basically the definition, which we don't need. Composites are more than two divisors. For example, which is the minimum, what are the elements like 4, 6, 8 and all those things are composites. We'll see that usually for composites, if the modulo prime, I'm saying about modulo n, that n if it is prime, then it will actually have certain rules that we can impose on top of it. We don't need the existing process to compute. We need some rules in order to find the multiplicative inverse, in order to find the remainders for that matter. Okay, so for that we need the formulas. Right. So, for example, this is again just a starting of it. What is the smallest prime number? The smallest prime is 2, which is divisible by 2 and by 1. And if you consider the list the number of primes smaller than 10, what is happening here? Even the brightness is low. Why it is happening like this? Is it visible at the back? I think it is, but it was relatively brighter actually. Unfortunately, last day also went fine. Anyway, so when we took into consideration the number of the list of primes smaller than 10, we can have 2, 3, 5, 7, which are the prime numbers along with it. And you can see it is interesting to note that the percentage of prime in the range of 1 to 10 is around 40%. So let it be. And also if we observe the last line, GCD of 1, okay, GCD of a comma b equals to 1, then we call the two positive integers co-prime. Now this co-prime word will be used. Now if you observe that this GCD equal to GCD a comma b equals to 1, this we had already used a long time back when we used the multiplicative inverse, the Euclidean algorithm. There also we had used this. Alright. But now we are telling that those two integers for which this is 1 is given by co-prime. They should be co-prime because these conditions will be important leading further. Alright. So again, how do I find the prime numbers given a particular that whether it is a prime or not? One of the process, the generic method for using it, one is that if I take the square root of it, okay, so if you suppose you take 97, you check that 97 if it is a prime or not. Okay, this is just a preliminary part of it. We will lead to the other part. So what we will do is we'll take a square root of it. So we'll take around 9. So 97 square is the flow function in 9. So that flow, the prime less than the 9, the number 9 are 2, 3, 5 and 7. Now you have to check that whether this 2, 3, 5 and 7 divides the 97. So you can see, we need to see if 97 is divisible by any one of these numbers. Now you check 2, 3, 5, 7 is not dividing the 97. So we can say that 97 is a prime. This is one of the very oldest way of doing it, but it is not actually correct. Even then this process is a bit lengthy and it's not a proper process. You can see 301, it is a prime or not. What we have to do, we have to take square root of it. We have to take these floor concepts. Let's see the floor of 1 is 17. Now you have to find the number of primes between the first number to 17. And these are the numbers which come 2, 3, 5, 7, 11. Now you have to make sure that you divide 301 by each of those prime numbers. Okay? And if you find that anywhere this is getting divisible, then we can say 301 is not a prime or it is a prime. If you also that both cases it's fine. 5 do not divide 301, but when you come to 7, it is divisible by like 301 is divisible by 7. So we can say that for 301 it is not a prime. But as I said, this is all like existing techniques which are relatively okay with small numbers. But again, as I keep on saying that this process are involved with cryptography or with information theory, where you are sending a lot of data and you are handling a lot of data. Where the data or the group set or the fields that you are working on has a lot of information. In those cases, the finding prime, if at all it is a prime number or not, these methods won't be sufficient. Even this can be extended to a bit when we consider the tabulation which was done by Theorem. What he did actually, that he proposed a formula for a given number. Suppose for example 100. What we have to do is we have to arrange all the numbers starting from 2. So 2 to 100, all the numbers should be arranged one after the other. Then square root of that number is 10. So within 10, the same way, how many number of primes we have? 2, 3, 5 and 7. So what he proposed is something like this. I'll go to the next slide and then I'll show you. What he proposed is that same process, cross out all the numbers which are divisible by 2. Alright? So cross out all the numbers divisible by 2 if you observe. So except 2 itself. So you can see 4, 6, 8, 10, 12, 14 and so on. They have been crossed in that way. Same way, any numbers which are divisible by 3, divisible by 5 and divisible by 7. So like that whole tabulation that you observe has been made sure there are some numbers which are cross. This one is cross. So leaving out all this, whatever you are left with the elements, those will be considered as the prime numbers. Or the leftover numbers are called prime. This is the set of 100. So this is about the total number of primes that is possible for the number 100, n equal to 100 in this case. So if you have a larger number, you can fix another table like this and you can go on doing the same thing based on the number of primes available with the square root of that number. Okay. But again, as you can see, this is a laborious task of doing it and it is again very old method and we cannot utilize properly effectively. So that is where the algorithms or the rule for the Fermat's and the Euler's theorem comes in. Alright, to find the prime and their properties, to utilize the properties of them. So these are all preliminary things. So please make a note of this. This is where we start actually our discussion. So Fermat's little theorem is a process in which we define a particular formula that if P is prime and A is an integer, please make a note of this. If P is prime and A is an integer and the condition given such that P does not divide A. This is one added conditions provided. Such that P doesn't divide A, then we can represent with the format first format of A to the power P minus 1, please make a note, A to the power P minus 1, okay, is congruent to 1 mod P. Okay, so if you have A is a number and you have P minus 1 where P is the prime number and you can see mod of P. So that's what I was talking about. The mod N which was there up to this point, now we are only focusing on the primes. So P, it should be mod P in this case and where P is a prime number. So the first element, the first version of it is A to the power P minus 1 congruent of 1, which basically means A to the power P minus 1 divided by mod P or divided by P, the resultant remainder should be 1. So that is what the idea is. But if you see the second version actually takes out the condition also that A should not be divisible by P, and you can see this. What man, this is creating a lot of issues it seems. One minute, give me 1 minute. There's a problem with this cable. There's a problem in that port. And the second rule you can observe, it is not imposed. So the formula becomes A for B component with A mod C advantage. C advantage. If you are given any integer and you are given a P which is sufficiently high and you have checked it, then I can't finish. So what you can say is that if this is P, if this mod is prime, then basically your output will be A. Okay, so the whatever be the integer value that can be considered as the remainder. So that's 1 minute. For a given instance, you have a P or the number as prime, you can find out quite easily that the output will be 1. The point is here, you don't need to compute at all. If your modulo operator is 5 and you can represent that according to the Fermat Little theorem, you actually without even computing, you can say that the resultant will be 1. Or for that matter, if you 5, so if you suppose 5 to the power 10, or 5 to the power 11, you have, where P is 11, which is the prime number, then we can say that if suppose I want to find 5 to the power 11, mod 11 for that matter, the remainder will be the element itself. So 5 should be the answer. Understood? So in that way, we'll see the example after this. So in this particular case is very important because leading towards the finding the number of primes. Because as I said, the process that is prevalent, the existing techniques of tabular column or finding the square root and all those things, that is not at all applicable for large numbers. So you have to use these formulas at some point to get the number of primes. Suppose the Euler's theorem will give you the number of primes which are possible. Okay. Or in this case, you can check that for this cases, suppose how do you find the multiplicative inverse of a prime number for that matter. Okay, so all those cases, these formulas are useful. So let's see with an example. Suppose this is your example given. So 6 to the power 10 mod 11. What is the result of? Now, if you compute normally, like for example, you take calculator, you take 6 to the power 10, then you divide by 11, take the remainder, and all those processes. Instead of that, if you are representing this 10 and 11, you can say that this is my P and this is my P minus 1. So, as per the Fermat's first theorem, we can say that very clearly this will be, as you can see, the first version of it, that P is equal to 11 and this is P minus 1. So the first law is that, as per the first law, the output should always be 1. So without even computing anything, you can just directly say that the answer is 1. Understood? So that is the application. Without this Fermat's theorem, you have to compute. And now with large number of, like when the prime number is typically large, and you have a power which is even larger, then it's very impossible to calculate even in calculator. You will soon find. I'll give you some examples. You will soon find that even in calculator, this is not a very comfortable scenario. Only if you have used this formula, you can able to solve. Similarly, you can see 3 to the power 12 mod 11. Now, in this case, if you apply, you can say that it is not actually following correctly. Why? This is P plus 1. Your P is 11 actually. You check here, your P is actually, so your P is over 11, right? So P is 11, whereas this one, which should have been 10, is now basically P plus 1. Right? So that's why it is not applicable at this point. So what they're doing is, basically, you can see that the last step over here, 3 to the power 12 is divided into or factorized into something like 3 to the power 11 multiplied by 3. Please make a note of this particular arrangement. It will be useful sometime. 3 to the power 11 multiplied by 3. Why actually? Because now we are going to decompose it some way. That 3 to the power 11 mod 11 multiplied by 3 mod. Now 3 mod 11 is very easy. We can say it is 3. Very simply. 3 to the power 11 mod 11. What is the, or what we can do on that? 3 to the power 11, do we need to compute 3 to the power 11 then divide by 11? No. Because if you observe that, sorry, if you observe that this part, if you observe this part is nothing but a to the power p congruent to a mod p. So what y meaning is 3 to the power 11. So 5, so 3 to the power 11 and this is mod 11. So this whole thing without even computing you can say the output of this will be because your a is computing. What I'm trying to explain. Instead of computing this part, you can apply the second rule because this is a to the power p congruent of mod p. If it is, then the output will be a. Here our a is 3, 3 to the power p, that is 11, mod of p. So this whole thing is nothing but related to second rule. So the output of this will be a. So we can say, you can see 3 into 3, this line, 3 into 3 mod of 11. So the answer is 9. So the point is you can say, sir, we can compute it and we can say that what is the final result of it through calculators. But let's see if you can do this without using this rule. Let's take an example. Let's take an example. Can you compute, okay? Can you compute 4 to the power 532 mod of 11? Suppose this question, the question is to find the result of 4 to the power 532 mod 11. Now, as per the rule, mod 11 to mod p, p is a prime number, that's fine. But you have been given such a large value that if you take it in a calculator, 4 to the power 532, it won't come. Okay, so that's the problem. That is where you have to apply the performance theorem in order to decompose it into smaller powers and compute the final result of this. And as I said, these are all applicable for the asymmetric key encryptions, which we'll learn again in fourth module, in fact. So if suppose this is the given question, so what we are trying to do is, so we can say our A is equal to 4 and our P is equal to 11, right? So if that is the case, let's have A to the power P minus 1, which happens to be 4 to the power 11 minus 1, 4 to the power 10. We can write it this way. See, this y I'm trying to write. 4 to the power 10, if I have, what is my mod value? 11. So if we don't know Fermat Little theorem, we cannot claim this. Why I am claiming this? This is p minus 1. This is my p. So as per the first rule, we can equate this one. So what is the advantage? For this 4 to the power 532, if we can arrange it in a way where this 4 to the power 10 will come, then we can replace 4 to the power 10 mod 11 as 1. I'm repeating it once again, what I exactly am trying to say. This is a to the power p minus 1, we are applying the first rule, right? P is our 11 and 1 to 4 to the power 10. Now we are equating a to the power 5 minus 1 as per the first law. 1 congruent of 1 mod of p. First rule, right? So we are representing it. My logic is, if we can represent this 4 to the power 532 in a way where this 4 to the power 10 mod 11 will come, then we can replace that whole term by 1. See for yourself how we are trying to do. So let's have 4 to the power. See this carefully, okay? We'll see another with another example. 4 to the power 5 32. This is what we have in the left hand side. So if I write it as 4 to the power 10 into 53 multiplied by 4 square mod of 11. See what I'm trying to exactly establish over here. 532 is there. I'm repeating it once again. We are trying to achieve so that this 4 to the power 10 appears somewhere. So the only option is that if I take 4 to the power, like 532 is like this, we can say the power remains 532. But here we have 4 to the power 10 as a factor. And we already know 4 to the power 10 mod 11, the resultant is 1. So we can say, we can write this way as if we are writing, this is internally happening, okay? This is internally which is what is happening. So this part mod 11, 4 to the power 10 mod 11 is 1. 1 to the power 53 is 1. Understood why we are using the formula? 1 to the power 53 is 1. So whole of this thing is 1. I am not sure whether you are able to get it or not. So the question is 4 to the power 532. This is 4 to the power 532. 532, 4 to the power 532, even if you do it in calculator, the answer won't come. So what we have to do is, we have to make sure it decomposes in a way such that it is calculated. So how we are doing it? We are replacing this 532 by the power 10 into 53 and we are dividing this by 2 segments. Can you understand this 532? This is 530 and this plus 2, so 532 total. Now 4 square is fine. 4 square mod 11 we can compute, no problem. 4 square mod 11 we can compute properly. This one, we are making a bracket 4 to the power 10, 53 mod 11 because this mod 11 comes somewhere here internally and this is separate. Now this part, if you leave out this power, 53 to the power 53, what it means? 53 times it will be multiplied. So basically this is 4 to the power 10 mod 11 repeated 53 times. Now 4 to the power 10 mod 11 from the Fermat's theorem, the resultant is 1. So basically this whole thing is 1 to the power 53 as it is. Right? So this part we don't need to compute at all. This whole thing is nothing but 1 multiplied by 16 mod of 11. 4 square is 16, 16 mod 11. Now 16 mod 11 is very simple. So we can say the final answer is 6. If you are not using this formula, you are not going to calculate properly. Correct? 16 mod 11. 16 mod 11. Final answer I am writing by. This part is 16 only, no? So 16 mod 11 like this it will come. Something like this. Yeah. So anyway, so 16, basically what we mean is 4 to the power 532 mod 11 is equivalent to 16 mod 11. But if you can only do it using the application of the Fermat theorem. Am I clear with this? So the point is, 2 things to know. First thing is, you have to represent that using the first or the second rule based on your choice. Then, you have to make an equation ready which you can utilize sometime later for the given question. So keeping that in mind, can you do this second one? 2 to the power 16 mod 17. This is very simple in fact. 2 to the power 16, or let us make it, no, don't take it, 2 to the power 50 mod 17. Take this example. The question is 2 to the power 50 mod 17. 2 to the power 50 mod 17. Apply the formula here and find the answer to this. Let's see whether you are able to understand this. In this case, your A is 2 and your P is 17. Huh? Correct. Can I switch to previous question? No, I can't because that's being erased. Why? You tell me what happened. You want the answer or something like that? So, why it is 4? So, A is equal to 2 and P equal to 17. So, as per the formula, again if I write A to the power P minus 1, 2 to the power 17 minus 1. So, 2 to the power 16 congruent of 1 mod of 17. This is what we are trying to write. Right? This is with respect to find. So, anywhere, for 16 mod 17, you can replace that by 1. Now, you have to arrange 2 to the power 50 in such a manner such that this 2 to the power 16 comes somewhere. You have to arrange it accordingly. So, how you have divided it? 48. 2 to the power 48 plus, like, multiplied by 2 square. So, 48 plus 2 is 50. Now, that 48 can be replaced by 2 to the power 16 cube. So, maybe I will just write the first step. Oh. So, maybe I'll write it over here. 2 to the power 50. So, maybe it can be written as 2 into 2 to the power 16 cube multiplied by 2 square. This is how we are writing. Now, for mod 70, we can replace that by 1. So, that 3 times will be 1 by 2 square is 4. 4 mod of 17, your answer is 4. That's why many people are given the answer. Okay. So, the advantage of this rule is computational challenges are reduced significantly if I apply this concept. Any doubt with this? Anyone? Because this forms the basis of the next function, which is the Euler's phi function. Okay, let's see whether we can finish that Euler's phi function also. But before going to that, let us take the second element of it, which is another part of our discussion, which is the multiplicative inverse of prime. For example, you can see finding the multiplicative inverse is very quickly, we can do it using the formula as given over there. So please make a note of this. We'll see a specific question on this. A inverse mod P. A inverse, suppose A inverse, directly we are trying to find inverse. It's different to that of the finding the integer values. Okay, the normal example that we have done for multiplicative inverse, it was like 2 multiplied by 3. Find the inverse of 2. But here the value over here itself is inverse. Find the value. What is the inverse of A inverse? What is the value of A inverse? Based on the formula. So, the formula is given by this, that P is the prime number. Now, you can also that what we can do is that for example, A inverse mod 17. The answer will be 15 mod 17. Now, how we are getting this done? Okay. So, for that, I'll take some time to discuss this. Because normally, if you take 8 to the power 15 mod 17 till this point, suppose you take up to this point, 8 to the power 15 mod 17. Calculator, can you do that? 8 mod 17. Up to this point is nothing but decomposing with respect to this formula. Can anyone quickly do it? 8 to the power 15, what is the value you are getting? 8 to the power 15. Can anyone please do it? Into 10 to the power something, right? So it's a huge number. So we cannot really do it in a calculator. Normally we cannot do it. So the process is very simple. Okay, so let's see how we are going to do it. So let's take this question itself. 8 to the power 8 inverse, that's how it is mentioned. So I'm starting the question from the point. So this is given a mod of 17. Okay, and this we have already represented it as in terms of 8 to the power 15 mod 17. This is keeping the formula intact. So this is where we stand, 8 to the power 15 mod 17. After application of the formula, a to the power p minus 1 congruent to a to the power p minus 2 mod of p. So that is where we stand. Now, as this is not computed, like it is not a feasible solution in terms of our calculation, what we have to do is, we have to decompose it as much as possible with respect to prime numbers. For example, we will divide this 15 into 8 to the power 7 multiplied by 8 to the power 8 mod of 17. So that's how we are trying to utilize it. And finally, for this 8 to the power 7, can you calculate now? 8 to the power 7? 8 to the power 7 mod 17. What is the value you are getting? Please compute 8 to the power 7 mod of 17 and 8 to the power 8 mod of 17. How much you are getting? So one is 15, one answer I got. 8 to the power 8 mod 17. Hopefully all of you know how to take the remainder and take the base accordingly. 1. It will come around 0.99 something, so it will approximate to 1. So 8 inverse of mod 17 is 15 mod of 17. The point is not about finding the answer. The point is how you are going to factorize here. If it was 15, it is relatively simple because 15 is okay, we can divide it by 17 by 8 and 7. But suppose I give you something which is a little bit weird in a way. Okay? In that case also, you have to make sure that by some means, you have to differentiate, you have to decompose the power to certain extent to reduce it the power in a way such that it is computable. So, taking that into account, can you do the second question which is given by 22 inverse? Please make a note. 22 inverse mod of 211. What will be the multiplicative inverse of it? 22 inverse mod of 211. I am keeping this answer, the solution in front of you so that you can able to do it. So the first that you have to consider is that this is my p. So apply the formula a to the power p minus 1 mod of p is equivalent to or congruent to a to the power p minus 2. Okay, so that please compute first. So that first line, maybe I'll just write it down over here. Yes, please. So, this one? Yeah, P. Alright. Normal calculation, if you are 7 divided by that of 17. Remainder, whatever you get, that multiply by 17 again. Get the mod of 8 out. 8 to the power 7, take the value, divide that by 17, whatever the decimal value you are getting, multiply that decimal by 17 once again, you will get it. That's how you try to compute the for modulo. Because you remember all the cases, whatever be the base, your answer should be within that period. Because we are using the modulo operator to limit the calculation that we had discussed in the very first few classes. Right? So compute this one. So here 22 is my A. So we can write this as 211 minus 2 mod of 211, which means 22 to the power 209 mod of 211. So this is where we stand. 22 to the power 209 mod of 211. That you have to like this. You have to fraction divide it such that you are able to compute the final answer. Just try it for 2 minutes. Let me take the attendance and then I will come back to you. help me finding the answer. To the power 209 is present, right? So let me quickly refresh this page and show you that how we are going to do it. If time permits, next day we'll come back and we'll solve a few more. See for yourself and try to practice it actually. So now we have 22 to the power 209 mod of 211. Okay. So the point is we have to make it as much small to the power element. So one of the arrangement can be 22 to the power 4 multiplied by 22 to the power 5 into 41. See for yourself if you are able to understand. This 209, just like the previous few examples where the power was little smaller, we were dividing it into two halves. We are factorizing it kind of two halves. Here, we are trying to add 22 to the power 4. We could have taken something else also. Don't tell me that this is the only solution. No. There can be other solution also. Like for example, you could have taken 22 to the power 100 multiplied by 22 to the power 109. You could have taken that. But 22 to the power 100 is again, it's a very high number. So you have to take multiple steps to find out 22 to the power. So what my observation is for the given questions, whatever I came across, any one of the factor make as much small as possible. At least keep that because 22 to the power 4 we can compute easily. 22 to the power 4 you can have calculator and you can find out the answer. What we have is this 22 to the power 5 that is in bracket. Can you quickly find me 22 to the power 5? What is the answer we are getting? Take mod of 7, mod of 211 along with it. So this will come with 211. So I'm keeping 22 to the power 4 as it is. We will compute it later also. That's not a problem. Now, whatever is inside the bracket, that should be to the power 41. Can you quickly give me the answer? 168. So now you are in a position, this is 168 to the power 41 mod of 211. Right? Even now, the scenario is not that easy because 168 to the power 41 is a big number. So you have to, sorry? Sir, 168. So what will you do? I don't know. Tell me. No, I mean, you take the mode of it, no? 22 to the power 5, what was the value you are getting? Divide that by 1. Then take the remainder, multiply that by 11, you get this one. Because again, remember, this value is within 211. 211 is the maximum set. So your answer should lie within 211. So now 168 will have 41. How you can divide that? How you can factorize so that this power becomes lesser? Any given idea can you? Anything? 4 into 10 plus 1 into 10. 4 into 10 plus 1. So basically, you can have one of this option as So you can have one of the option as where we are 22 to the power 4 multiplied by 168 into 168 to the power 4 to the power 10 mod of 211. Honestly, what I mean, this was already there. 168 to the power 41 was there. So I divided 41 into 40 plus 1. Now see, one numerical data of integer value we have already received. We don't need to do anything. Again, you have to compute similarly 168 to the power 4. Whatever the value you are getting, that you substitute over here. That will be to the power 10. So that 168 to the power 4 will come as 179. So maybe I'll just write it down again. 179 to the power 10 mod of 211. Now that 179 to the power 10, again that's a problem because that's a huge number. So what you can divide that into? 2 into 5, 179 square bracket whole to the power 5. Because 179 square is possible. Like that if you go on doing it, so I'm asking you to do 179 square multiplied to the power 5, 168 as it is, 22 to the power 4 as it is, this mod of 211. Now again you compute whatever the value of here to the power 5 and you go on compute. Again finding result, multiply is the divisor by 211, divide the 1 by 2, translating. The problem with this kind of question is that to how do I factorize this? So one of the rule, please remember, whenever you get that power to be pretty high, like in this case 457 or something, 453 something, or even here 22 inverse 211 is the base. Make sure that at least one of the factor has a less power, like 22 to the power 4. We started off with that, right? Keep that in mind. Otherwise, you are not going to find a right solution. You might find the right solution, but it will take long approach to finding. As I said, this is only one of the solution. It's not that this is the only solution. Remember, there can be other solution as well. How you are factorizing it, that depends. The faster you can do it. Okay, so next day when we come back, I'll take few more examples, and you will find that along with this, we will discuss the Euler phi theorem, okay, and the Euler's theorem, two separate theorems, and we'll see how that goes. Alright, thank you.